Alright, my dear students, so let's look at to one example, and you can refer to the textbook, page 340, problem 7.17. So for this case, we are given two types of current. The first one here, the line current, located at 1 minus 2, and we assume a very long line current. And also the other one here, we have surface current density given as 100 in z directions milliampere per meter. So you can define our types of current based on the units, right? If you see the unit of ampere per meter, for sure it is surface current density. Alright, now we are going to find the H that actually appear at this particular point, and we know that every single current, they have their own H. So for this case, we have two types of current, so by that we should have two value of H that comes from each and one of them. So we can simply write down here the H, right? The H at point P or point of interest actually is due to the H due to the first line current plus H that due to the surface current density. Okay, so the first one, the H that due to line current, can be approximately expressed using these equations because we assume that it's a very long line current, so we can use ACL for this case. So now we have the versions of equation I over 2 pi r in phi directions. So this is the equation for the case of very long line current, and we know that the R here is measured from the line that perpendicularly connected from the line current to the point of interest, and the R here given as such. So now let's find the phi component here. So the phi here, guys, can be actually converted to the x, y, z components based on this equation. Unit vector of line current cross unit vector of radius that connecting between the line to the point in normal. So we can find the AL, right? We know that the line current now actually flowing in positive z directions, so by that we should know that this unit vector of line must be in positive z directions. And now we are going to find the unit vector for the distance that connecting between this line current to this point of interest. So we just find the vector from this line to that point of interest. Let's say my R number 1, a vector, right? So to find the R vector, guys, we should have 2 points. So now we have this point already, 4, 3, and 2. Now we are going to find the point at this line current that make them in normal or perpendicular. So we can simply find the value. The point here become 1 minus 2. And how about the z? So to make it the line perpendicular, you must make sure that the z value at this line is same as shown here. So again, you must use a 2. Now they have a very long perpendicular line that joining between these 2 points. So now again, we can find the R vector, or R1, this one R1 is equal to, you can see 4 minus 1, we're going to have 3x component. 3 minus 2, we're going to have plus 5 y component. So from here you can find the magnitude of the distance given as 3x component, 3 squared plus 5 squared square root, and a half equal to 34. Right, that's the magnitude of this R. So if I want to find the AR, yes, we can find the AR here. Just taking the vector of R1 over its magnitude, so given as here, so 3x component plus 5 y component over 34 square root, right? That's the unit vector of R that actually joining from the line current to the point of interest in perpendicular form, right? So now we can just substitute the value of R here is equal to this R value, the magnitude, you can see, and I here given as such. So now to find the H due to the line current, just substitute the value of 20 pi milli, alright, so over 2 pi 34 square root for this one. And now the phi, just put all this thing over here. So I'm going to have here Z for the L cross the whole term here, which is 3x component plus y 5y component over 34 square root. And now let's perform the cross product between z and x, and also between z and y. The z cross y is going to have positive y, and the z cross y is going to have a negative x, right? So now you can simply simplify the equation, becoming this one. So 20 pi milli 2 pi 34 square root, and now I'm going to have negative 5 x component plus 3 y component over 34 square root. Guys, this is the value of the H that due to the infinitely long line current at these positions that exists at this P, or this point of interest, and you have ampere per meter. Okay guys, so now how do I find the H that due to the very large or infinite surface current density over here? So as we derived last time using ACL, we can simply use the simplified versions of equations to find the H that due to infinitely large surface current, as shown here. The H that due to the surface current equal to 1/2 Js cross An, right? Js here given as 100 Z milliampere per meter. So now the N here, guys, actually the normal vector that pointing from the surface current to the point of interest. So there must be a normal. So but this is the unit vector that pointing normal from surface current to the point of interest. So An here must be in negative x because they're against the x-axis there. So that's here our An. So but guys, we have here the Js here given as 100 Z milli, and then the An here, guys, we have negative x directions. So then we do perform the cross product between the Z and the minus x. Now we are going to have the output of this cross product given as so Z cross x gonna have y. So now you're gonna have a negative 100 y over 2. Finally gonna have a negative 50 y component milliampere per meter. Alright, so that's the H that due to this infinitely large surface current density. So now let's combine them to find the effective or resultant value of H from these both types of current. So we know that the H at P, as shown above, is composed of 2 H from line, also for surface current. So just add them up. So the first one here, the H due to the line current, and plus this one, gonna have the equation becoming finally 20 pi over 2 pi 34 square root negative 5x component plus 3 y component over 34 square root, and now plus negative 50 y component. So after you simplify, you can have this value. H at P is actually equal to minus 1.47 in x component minus 49.12 y component. The whole term now has a unit of milliampere per meters. Okay guys, so this is the final H value that actually exists at this particular point of interest. And we must know that this H value actually is come from these two types of current. Okay, so I hope guys you can try yourself and make sure you get the same answer as shown here. Okay, so thank you, all the best.